This is our second video for the hypothesis testing examples, and this one is going to start out on example number 2. So let's read the example again and remind ourselves what we discovered in the first of the series, the hypothesis testing video. The administrator of a nursing home would like to do a time and motion study of the staff time spent per day performing non-emergency types of chores. In particular, she would like to test to see if efficiency is up. That means spending less time on chores, by the way. And that testing whether efficiency is up is what formed our alternative hypothesis. And she wanted to see if it was up, the efficiency was up, meaning time was down, from a prior study that showed that the average was 16 hours that were spent on chores. So she wants to use a 90% confidence level in testing her claim. So I'm going to write down here that my confidence level is 90%. And remember, from the confidence level, we're going to find alpha. And that alpha is 1 minus my confidence level, which puts it at 0.1. Now once I have this 0.1, this 0.1 goes right here. And so that is what we're going to use to test our claim once we get the test statistic and then find the probability. So our sample information is what I need next. Now my sample information, I'll need a mean and a standard deviation and a sample size in order to create my test statistics. So my sample information, this one says that its sample of time and motion for 12 nurses, so I have n is equal to 12, showed that they had a mean time average, or an average time of 16.5 hours. So 16.5 here. And then their standard deviation for the sample was 0.75 hours. So what we're looking at here is how am I going to get my test statistic? Well, my test statistic for averages, right, is going to be either a t or a z. But which is it? Well, this one is a t because in is less than 12. So I'm going to get my test statistic being a t, and I'm going to find that test statistic by taking the sample mean. And so I'm going to write t here equals, and then my sample mean, which is 16.5. And then I'm going to subtract the mean of 16. And then I'm going to divide by the standard deviation of 0.75. And then divide by the square root of the sample size, which is 12. And then I'm going to get my t out of that. So this one I can see right at the get-go that it's not going to be a rejection. So we have 16.5, 0.5 minus 16, and that's going to give me 0.5, and I'm going to divide that by 0.75, and then I'm going to multiply it by the square root of 12. I think I've explained why I do that before. And this is going to give me a positive 2.3 1 approximately. Now, why did I say before that this is not going to reject? Well, this is a positive value. A positive value is over here, right? And a positive value is not in that rejection region. I can see without even going any further that this would be a fail to reject. But let me again reiterate how we would do this testing. This is the probability that a t is less than a 2.31. So where did the less than come from? Well, remember that the less than comes from the fact that this is less than. So we're going to do less than 2.31. Now, how do I find this probability? Well, this is a t distribution, so I'm going to use the t CDF, and I'm going to say, okay, my lower bound, -9, comma, up to 2.31, and then I'm going to find that probability. And so second function variables, t CDF, and I have a -9, comma, up to 2.31, and that value, I also have to have a degrees of freedom, and my degrees of freedom, remember, is going to be my n minus 1, so I'll also put in that degrees of freedom, and that would be 11, and that probability is going to give me a 0.9793. Now, you're seeing a huge probability here, and remember what we're questioning is that less than the 0.1 in the rejection region, right? So if my probability is less than the 0.1, that means it falls in this rejection region. It doesn't fall within that rejection region. We knew it wouldn't fall in that rejection region. So this decision is to fail to reject. So we're going to fail to reject the null hypothesis. And remember, that means that's to me the technical way of saying this, that we fail to reject the null. But then there is the conclusion that I would write, and the conclusion that I would write personally is going to state three main things. I'm going to say at the, and I state the confidence level, 90% confidence level, or if you want to state it in a different way, you can state this, which is called a significance level. So an alpha is a significance level, and this significance level is going to be 10%, sorry. And so if I wanted to state it that way, I could as well. So at the 90% confidence level, and then I state that there's not enough evidence because we failed to reject. There is not enough evidence. So it's not enough evidence. And then remember what we do is we will say what the claim was. So we'll say to support that time in motion is down. And you'll blah, 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 blah. I'm tired of writing and I've run out of room. So time in motion is done. So it concludes that hypothesis test. All right, now let's move on to our final hypothesis test. And this one is our two-tailed test. So in this particular one, let's go read the problem again. In a sample of 40 company cars, the average miles driven was 2,752 with a standard deviation of 350 miles and a 95% confidence level. So now remember, this 95% confidence level goes right here in the middle because this is a two-tailed test that the 95 goes in the middle. That means that half of the remainder goes on the left, just like a confidence interval, so 0.025 over here and 0.025 over here. So we're going to take that alpha and we're going to split it into both tails, just like we would with a confidence interval. So alpha is equal to 1 minus 0.95. And that is going to give us the 0.05, but it's two tails that we're dealing with, so we have to break it up this time. And remember, now what we're going to do is we're going to compare it, this alpha value, when we go down to our probabilities, we're going to compare this to 2 times our probability. That's how most people do it now because of the way technology does it. It can also be just compared to one of the tails, but that's not the typical way of doing it anymore. So now I need my sample information that's being held up to compare to the claim, and that was the information given first this time. So n was equal to 40, and the x bar was equal to 2752, and the sigma was equal to 350, and these are all in miles. So now the next thing I need to do is I need to compute my test statistic, and because I'm dealing with means again, right, the means I need to know, is it a z or a t? So in order to make the decision, because mu, right, z or a t, I need to go up here and look at the n. And because the n is 40, I'm going to be using a t, or excuse me, a z. And so my z is going to be looking like my sample mean, 2752, minus, and then we have the population mean, which is under the null hypothesis, the null hypothesis, 2600, and that's divided by the standard deviation, 350, divided by the square root of the sample size. So now I'll go ahead and compute this. So I have the 2752 minus the 2600, and then I'm going to divide that by 350, and then I'm going to multiply that by the square root of 40, and to 2 decimal places I get that this value is 2.75. So there's my z value. Now I need to find the probability of that. The probability of a z, now this is a positive value, and this is where it's kind of tricky because you've got two tails, right? It's like, oh, well, how do I find this probability? Well, this one is a positive value, so I'm going to say it's greater than. So because this is positive, I'm going to use the greater than. I'm using this tail up here. So I'm going to say it's greater than 2.75. Now, in order to do my p-value test to conclude this whole thing, I'm going to say that this is twice this probability so that I can then question if this is less than my alpha still. So that's what I'm going to do. So whatever I get out of here, I'm going to do 2 times this probability and then ask if it's less than 0.05. So remember, I do this by doing a normal CDF. And then I have greater than 2.75, so my lower bound is 2.75, my upper bound is 9, and second function variables, normal CDF, 2.75, comma 9, and then that's going to give me approximately 0.002997, so that's 0030. So this 2 times 0.003 is going to be 0.006. So 0.006, that is less than 0.05. And so this time around, we see that our decision is 2. And when it is successful, we're going to say we reject the null and we accept the alternative. So this go around, we're rejecting the null and we're accepting the alternative. Now our conclusion, the only difference in our conclusion is now that instead of not having enough evidence, we have enough evidence. So at the 90%, and if you're going to say alpha, 95%, you're going to say the significance level, you would use 5%, okay, even though it's a 2-tail and it's in each tail is 0.025, you use alpha as a significance level, but I'm going to use confidence level. At the 95% confidence level, there is enough evidence and that would be to support the claim that mileage is different from last year. Now we don't know if it's different bigger or different smaller. You can't make that claim. You just want to support the claim that mileage is different. So it looks like it's bigger, right? But you can't literally say that unless you go back and do another test. So we just say mileage is different. As I said before, it's really hard to write like this. So I'm going to end it just like that, that the mileage is different. And that concludes our 3 different types of hypothesis tests.